All right, folks, today we're going to be talking about two things. The first is finding the inverse of a function, and the second thing is using composites. So first up, to talk about inverses, we have to know what that means. An inverse is just taking a relation and switching the x and y. For functions, it's a little bit more complicated to find the equation for the inverse, and so on your note card I provided 5 steps to get you there. So you want your note card in front of you and go to where it says finding the inverse of a function. The 5 steps we're going to use start out with the sketch of the original graph. So our original graph here is a line. We're just going to sketch what it looks like. We know enough about lines to know that this starts at 4 and then goes up and right from there. Okay, simple sketch, doesn't have to be fancy, because what we're going to do on this sketch is just ask ourselves, does it pass the HLT? Because if we're talking about inverses and working hard to find them, we want to make sure that the inverse is a function. Well, the function test for a graph is using the VLT, but if we're switching the x and the y values, a vertical line becomes a horizontal line on the original, so we're using a horizontal line test to decide if the flipped version would pass the vertical line test. So horizontal through here, it passes. On your note card it says, if this does pass the HLT, we're going to give the domain and range. So under step 1, still domain and range of that function that you just sketched. So all lines, domain is all real numbers, range is the same thing. And we're on to step 2. In order to switch the x and the y, we have to see a y show up. So instead of f of x, you just write y equals. Then on step 3 is where we actually get into the math stuff. So we're going to trade the order of x and y. So x equals 1/3 y plus 4, and in step 4 you're just going to go solve for y because we like equations y equals. So first up on this one, we'd want to subtract that 4 over. So x minus 4 equals 1/3 times y. To get rid of this 1/3, we want to times by 3, but making sure we do that to the whole thing on the left. So this would be 3x minus 12, distributing that 3 through, equals our y. It does say on this same step we want to change this to the inverse notation for a function, and so that's the -1 power here. That just says the inverse of f of x. And that's our 3x minus 12. Then step 5 is just give the domain and range of the inverse. This is a line as well, but I don't want you to find the domain and range based off of this. I want you to use the original. Because if we did all our math right, the domain and range, because they represent the x values and y values on the graph, should just flip-flop places. So our new domain is this old range, all real numbers. And our new range is all real numbers as well. Now it's going to be very important that we switch those and not just look at the line because of weird graphs like the next one. Okay, so on the next one, let's talk about the original. We know the square root function kind of looks like a square root symbol. It starts at a point and goes up and right from there. So we're going to sketch it based on this -4. Using transformations of graphs is going to help us sketch these without using our calculator, but if you're ever not sure of what something looks like, go ahead and just type it in. So this one is moved to the right 4. So I'm going to write that this is at 4, 0 instead of 0, 0, and then it goes up and right from there. Now the reason I'm putting the point on there is because this graph does in fact pass the HLT, meaning I do want to find the domain and range for my step. With seeing this point, I know that my lowest x value is 4, and that is included on the graph, so I'm going to put a bracket, and then it goes off to the right towards infinity from there. Similarly, from the bottom, lowest number is 0, that's included, and it keeps going up towards infinity. Step 2. Again, from your note card, it just says replace f of x with y. So I'm saying y equals square root of x minus 4. And then step 3 is where you get to trade those places. So x equals big square root symbol y minus 4. Do pay attention to where your square root symbol is. You are going to see some that have like a plus or minus on the outside, and that will affect how you solve these problems. For this one, though, if we're just trying to get y by itself, we have to get rid of this root. There's nothing to add or subtract first, so we're going to go ahead and square both sides of our equation. The x squared comes down, On the right-hand side, the square and the square root cancel out, leaving with y minus 4. Then I'm going to add that 4 over to this side, so x squared plus 4 equals y. And then remember, they want to call it f to the negative 1 power, so that's the inverse of f of x equals, and just that x squared plus 4. Step 5, you're just going to write the new domain and range. And here's what I said was important. And for this, I'm going to show you the graph. You will never have to graph the inverse, but I want to show you for this one. So we just found out that the inverse was this x squared plus 4, which is a parabola that's moved up 4 places. So here's my parabola. But I want to talk a minute about something special with inverses. Because my graph over here wasn't awesome, I'm not going to actually use the line to talk about it a whole lot, but I am going to draw on something that happens. Okay, so this is the equation of y equals x, and I'm going to put it on both of these graphs. Every inverse will have this same pattern, and here's what it looks like. When you take the original graph and reflect it over the line y equals x, you should map onto the graph of your inverse. Now, if I look about a parabola, that is twice the size of this thing because my square root symbol only has a piece of that parabola. So this domain and range, why I'm telling you to just take these and flip-flop them, it does the work for us, saying that the domain should only go from 0 to 4, and when we do that, we get 0 to infinity, and when we do that, we get 4 to infinity for our range. So looking at this graph, I want to get rid of this part because I only am looking at 0 to infinity from the range of the original. And it restricts that for us so we don't have to think ahead on that. And really, this is the only type of equation that has that happen. But just use the original, not what you would think that the inverse is supposed to look like. Okay, with this line, I told you it'd be a little bit messy because it was rough, but if you think about it, negative 12 would be way down here, slope of 3, something like that, and you can see the reflection happening there as well. You do not have to graph the inverse. That's why we use the HLT on the original, so we can avoid graphing the inverse. Okay, but I did want to explain why this domain and range was just switching from that first point. Okay. Next up, we're going to look at a parabola itself. This is x squared minus 4. So in our step 1, when we sketch this thing, our parabola has moved down 4. So there's my u. And this point is 0, negative 4. Okay, with this one, our graph does not pass the HLT. That means that the inverse would not be a function. We could find the inverse, but it wouldn't be a function, which means it's not very useful for us. So what we're going to do here, in still step 1, we're going to say that f of x fails the HLT. So the inverse is not a function. And we're not going to waste our time going to find it. Okay. On step 4, we've got a hyperbola, or a rational function here, any way you want to look at it. But from our parent function 1 over x, this a value just stretches. It doesn't affect domain and range or the graph, so we don't need to worry about it. But remember, if this plus 3 is on the bottom, we have a translation. So we're going to start out with our graph. We know that asymptotes start at 0 and 0. This plus 3 means it's gone to the left 3. Because I don't have anything to the side, I'm still at 0. And let's go ahead and label these things on here. Just like with that point, it's going to help us with our domain and range. And then because hyperbola has branches diagonal from each other, we can go ahead and throw those on there. One at the top right, and one diagonal from it. This does pass the HLT. Okay, even here, it's hard to see, but it does decrease, decrease, decrease towards that 0 forever, which means we will have an inverse that's a function. Domain is everything except for negative 3, so negative infinity to negative 3, union, negative 3 to infinity. our range is -infinity stopping at 0, picking right back up at 0 towards infinity. Then step 2. Remember, we want to replace that f of x with y. So I'm just writing y equals 4 over x plus 3. Step 3 from your note card is just trade at the x and the y. So that's x equals 4 over y plus 3. And then we have to solve for y. There's a couple different ways to do this, but I want to encourage you to think about it this way. We have right now this x on the top at the left, and we've got this y plus 3 at the bottom. And what we can think of is the left-hand side as a fraction and the right-hand side as a fraction. Okay, you can cross multiply to solve, but the problem with that is then we're taking this x times this y plus 3. Same thing if you just think about getting rid of that denominator by multiplying over. When we see parentheses, we want to distribute. The problem with that is when you take x times y, that's not helpful. So instead, think of these as, I need this y to be on the top of the fraction, and it's not. So what we're going to do is actually just reciprocate both sides of the equation. This is 1 over x equals y plus 3 over 4. And why that works is, if you think about cross multiplication again, we would have the same parts going towards each other as the previous step. The reason it actually helps us is now that y is in the numerator, timesing by 4, timesing by that denominator, does not cause problems like it did previously. So this is 4 over x equals y plus 3, and then you just subtract that 3 over. So 4 over x minus 3 equals y. Okay, just to show you here, and you can just watch if you'd like, this is the same thing as if you had x equals 4, y plus 3, and you wanted to multiply by that y plus 3 on both sides. Okay, our brain isn't very good at not distributing, but that's exactly what you would have to do if you use this method. Okay, we would want to leave it as this, and then because that's times, we could divide it over. If we reciprocate both sides, we get that taken care of without the extra step. Okay, so when you have fractions and your variable is in the denominator of the fraction, you can flip both sides and it's valid. Okay, so from there, y is by itself, and in the next step we need to, or in this same step, we want to name it f inverse instead, and just call it that 4 over x minus 3. You'll notice that's still a rational function, just where the variables show up and where our numbers are look a little different. But our step 5 is the same as it always is. You take the domain and range from up here and you flip them. So the domain is -infinity to 0, union 0 to infinity, and the range is that everything but -3. And you'll notice with your equation, because these are a little bit trickier to solve, you can check yourself with this because nothing weird happens like it does with those square root problems. The x in the denominator says you should have a restriction at 0, and we do. And this -3 means our horizontal asymptote has moved down 3, and you can see that from the range as well. Okay, so these should correspond to each other when you're all done. What I want you to do now is take a look at 5 and 6. I want you to do all 5 steps, and when you're done, you can check yourself with the video. Okay, so pause that right now and take care of 5 and 6 for me. Okay, 5, again, you can just flip-flop both sides. Okay, so the y plus 4 goes on top. I skipped some steps here, but that would look like 1 over x equals y plus 4 over 5. Multiplying that 5 over leaves the y plus 4 by itself for you to be able to solve. Make sure in your step 4 you don't forget to rename it, that f inverse, and our domain and range just switch from the original. Okay, remember, if you don't know what the graph looks like, you can type it in. Be careful with these that anything, you've got 2 things in a fraction need to be in parentheses when you type them in, and that'll show you the -4 is really to the left. On number 6, you didn't have to work too hard because our absolute value looks like a V. Similar to a parabola, it does not pass the HLT. So the inverse is not a function, and you just have to say so. All right, on the back side, we're going to move on to the second thing that we're going to talk about, and that is composites. So you've seen this in Algebra 2, but I want to remind you of what this means. This open dot means composition. It does not mean multiplication. It is open for a reason. And the circle actually means following. So when we see F of this open dot and then G, that says F following G. And a lot of times they read it just of, like F of G, or F of G of X, as in the problems below, but it really means following. So this says F following G, meaning G goes first, and that's how we approach this problem. We're going to break this into two pieces, the part with G and the part with F, and we're always going to start on the inside or last. So this reads just G of -2, and we know how to approach that part. It just says take the G function and plug in -2 instead of X. So over here, we're replacing this X and this X with the -2. First part's already done for us. The second would look like -2 minus 7, and that equals -9. Once we have that -9, that is in the place of that G of -2, so we can rewrite it here. And now it says F of -9, so that's our second part. We're going to look at the F function and plug in -9. So this one's got an X here already taken care of, an X getting squared, and an X over here. So I like to use parentheses when it's not just addition or subtraction. So this would be 2 times -9 getting squared plus 3 times -9. And you can do this in your calculator or in your brain, it does not matter. If you're using your brain, be sure that you're doing order of operations correctly. So taking your -9 and squaring it first. That would be 81 times 2 is 162. This part is -27. So your final answer, and I want you to write it directly next to this A value, is 135. Okay, if you don't write it next to that, you have to rewrite it F of G of -2, and I leave off the extra parentheses, equals 135, to name what it's talking about. Okay, if you want to use your calculator for that, that is fine. Just make sure your negatives are in parentheses. That matters a bunch when your calculator is doing the work for you. Okay, over here, same process. We're starting with the inside, or the last part. We're looking at F of -2 first. So the F is our function, and instead of X, we're placing -2 there. So 2 times -2 squared plus 3 times -2. Okay, again, order of operation matters. This is -2 squared is 4, times 2 is 8. 3 times -2 is -6. So the first part is just the number 2. So you can go and cross that out and replace it just with the number 2. From there, you have G of 2. If it helps you to just draw this arrow to the next part, you can. Because that's all we're doing, is we're going one part and it places it into the equation of the second part. This one says just X minus 7, so for us that is 2 minus 7. So our final answer is -5. Again, if you don't put it right next to the original, you must rewrite it. G of F of -2 is -5 for our final answer. Okay. Part C and D, it's easier to set up, but usually more challenging to simplify. Here's what I mean by easier to set up. G of X is already done. It says plug in X. Well, X is already plugged in, X minus 7. So this whole thing gets to be X minus 7. And because this is sometimes messy, I usually don't write it above. I'll just bring it down. F is left, and instead of G of X, I'm writing X minus 7. And here's why it's a little bit messier. I'm replacing, instead of with a single number, a whole expression. So in the F equation, all of these X's get that big X minus 7 mess. So 2 is outside, then X minus 7 gets squared, and then plus 3, Again, instead of x, I'm writing the x minus 7. And so we have to simplify this, and it's not as easy as with just regular numbers. Your calculator cannot help you with this. This is all you. We've got to square this, which means really foiling. So if it helps you to write it out twice, please do that. And I'm going to go ahead and distribute this 3 through because I can. 3x minus 21. So here, the 2 stays for last. I want to do x times x is x squared. And then outside is minus 7, inside is minus 7, so that's minus 14x. And then negative and negative makes it positive 49. Just bringing down the rest. So then every number gets multiplied by 2. That's 2x squared minus 28x plus 98 plus 3x minus 21. And then we just have to put everything together. 2x squared is the only squared term, so it goes first. And then we have a minus 28 and a positive 3, so minus 25x. And then a positive 98 and a negative 21, so that's a positive 77. And that is your final answer for that one. Now, because these are kind of messy, I want to show you how you can check them using something up here. Okay, the whole idea of composites is it takes 2 steps and put them into one. So while this caused a lot of work, it actually simplifies the question from up above if we let it. So that wanted to find f of g of negative 2. Now that we know the composite function, we should be able to just replace our x with negative 2 and get the same answer as we did above in 1 step instead of 2. So I'm just going to show you typing this in, the negative 2 going in place of the x values here, and we should get the same thing as what we got on part A, and we do. Okay? Next thing we're going to do is with f of x. Usually if one's super complicated, the other one's not as messy. Again, instead of f of x, you just write the equation. So for us, that's 2x squared plus 3x. And we're putting that into g. G says take that and subtract 7. So for us, it'll look like 2x squared plus 3x minus 7. And there's nothing to simplify. That's literally done. Same thing, if we would take this and plug in the negative 2, we should get the negative 5 as above in 1 step instead of 2. Last thing we're going to talk about in regards to these composites is domain. So we want to talk about the domain of this function, and it's actually done in 2 parts. Here's how it works. The first thing you need to do is check out the domain of the function inside. So in your first step here, you would look at what's inside. So we're saying we're plugging in x minus 7. Because that x minus 7 doesn't have a square root symbol or dividing by x, then the domain has no restrictions. It's all real numbers. Then the second thing we want to look at is our final answer. Our final answer is a quadratic, which has a domain of all real numbers, just like a line does. So our final answer, our domain is all real numbers. The reason why that's important is because when we're talking about composite functions and their graphs, if this has a restriction, then we can't plug in any number we want and find the answer. It would come up as undefined. So we're just listing any potential problems. And this domain has none. Okay, when we're looking at this one, the same concept happens. The original is a parabola, so there's no restrictions to parabolas. Domain is all real numbers. And it ends up being a parabola when we're done as well, so domain is all real numbers. Again, the only time you're not going to have all real numbers is when there's a divided by x, because that causes a vertical asymptote, or a root, which means it starts at one number and goes on. It doesn't have every number work. Okay, and we'll see that happen on the next example. All right, number 8 here, we've got x squared plus 1, and we've got the square root of x minus 7, and it's just asking us for the composites. I want you to pause the video and see if you can plug those in for me. We'll talk about the domain together. All right, so this one has g inside, so that would be f of the square root of x minus 7. So for us, the square root of x minus 7 gets squared, and then we add 1. A square and a square root cancel out, so I've got x minus 7 plus 1. So my final answer is x minus 6. It ends up being a line. Okay, way basic equation for us to simplify if we're talking about like f of g of 2. This one, g goes on the outside, and then I'm plugging x squared plus 1 inside. So this would be the square root of x squared plus 1 gets a minus 7. And we can simplify this one as well to x squared minus 6, but because that is not something that we can factor, you cannot simplify. Something super important, plus or minus inside a root, you cannot split up, not fair game. So here, we're leaving it as x squared minus 6, and we're going to go talk about domain. So remember, there were two things you're supposed to check. The first is inside. A root function looks like starting and going to the right. That means it's not all real numbers. Only numbers from 7 on would work here. Remember, a minus 7 changes this to the right 7. Okay, so this isn't there. So our domain here is at 7 to 0 to start out, or to infinity to start out with. Okay, then, even though it says it's a line, we still have to use this 7 over infinity. And it's kind of complicated to think about because a line definitely does not look from 7 to infinity. But what I want to do is explain this using a graph. So grab a calculator for me. Pause the video if you need to grab one. And what we're thinking about is the composite function. Before it's simplified, this thing looked like the square root of, so we're going to type that in, square root of x minus 7. And then that gets squared plus 1. This was the original before we simplified. And if we hit the graph, you should be able to see that it's really going only from 7 to infinity based on what we plugged in. Okay, so there's our line, but it starts after 7. Okay, super important detail. Second one over here, we also have restrictions to worry about. On the inside, x squared plus 1, that's all real numbers. There's no issues there. However, with the leftovers, because it's a root, we know there's going to be restrictions. Okay, this one's a little bit different though because it's an x squared underneath this square root, and you've never seen a graph like that. If you're not sure, we're just going to type this thing in. Okay, we know there's no restrictions from the original, so we're just going to type in what we had. Okay, so we've got the square root of, and then inside we have x squared minus 6. And then we're hitting graph. So it looks like we've got negative infinity to some number and some number to positive infinity. We can find those numbers really easily based on what we know about regular square root symbols. The reason this was 7 is because if you set x minus 7 equal to 0, we get positive 7. We're going to do the same thing here. X squared minus 6 equal to 0. Add that over, and then take the square root of it. So we've got negative infinity from our graph, we're just looking at it, to this first answer is the negative square root of 6. And then the second part is the positive square root of 6 to infinity. Okay, you do not need to know that the graph looks like this. Okay, but hopefully you see that's the positive square root and the negative square root. That's really happening. Okay, but you do need to be able to find those numbers based on what the graph looks like. Okay. Last thing we're going to do is put together the first part and the second part, and the reason composites are going along with inverses today is because we can actually use composites to determine whether functions are inverses of each other. So at the top, here's what has to be true. If you take f of g of x and you take g of f of x and you simplify them, and if they both equal x, then we have inverses. So what we're going to do is take a look at each of these and see if they simplify to x. So first up, f of g of x. Remember, this says put g inside. So this would look like f of 2x minus 4, which for us looks like 1/2 times 2x minus 4, and then on the outside we have a plus 2. And then we just go simplify. So 1/2 times 2x is x, so that's so far so good. Second part is minus 2 when we distribute, and then plus 2, it simplifies to x. So we're going to f of g of x equals x. So far so good. Second part, we're going to go the other direction. G of f of x, and that looks like g is outside this time. Instead of f of x, we're writing the equation 1/2 x plus 2. So this is what we need to see in this second part. So 2 goes outside, 1/2 x plus 2 goes inside, and then this equation has a minus 4 on the end. And we simplify. X plus 4 by distributing, minus 4, those cancel out again, so that equals x as well. We just used composites to show that the f of x and g of x were equal, and because f of g of x was equal to g of f of x, and they both equaled x, we can say that the equations are inverses. So I want you to say, therefore, f and g are inverses. Okay, it's like a little proof. Both of them have to be true for the inverses to happen. Okay, so let's look at this next one. We want to take a look at f of g of x. And it doesn't technically matter which one you start with. I just like to go in alphabetical order. So this one, f is going outside, so 3, and g is going inside, 1/3 x minus 6. And then we distribute through. This says x minus, oh, I forgot on the outside, plus 9. So this says x minus 18, then plus 9. So this simplifies to x minus 9. That's not good so far, meaning we can stop. As soon as one of them is not equal to x, these things cannot be inverses of each other. So f of g of x, we'll just say not equal x. Therefore, f and g are not inverses. Okay, last one here. I want you to pause the video and try. I'm going to give you a little hint here. Make sure that wherever you're putting your inside function, it's going entirely in the denominator. It might be a good idea to put parentheses around what you're plugging in to make sure that you don't mess those up. So, first one here. In the f function, it would look like 3 on top still. But instead of x, I'm writing 3 over x. Okay, that's the same thing as 3 times the reciprocal. Okay, 3 divided by 3 over x is 3 times x over 3. And then those 3's cancel out, leaving you with x. G of f of x actually looks the same because these were the same function, meaning they have to simplify to the same. You don't even need that extra step. If this step looks the same, your answer has to. So, by that math, f of g of x was equal to f of g of x. Oops, sorry, g of f. Which was equal to x. Therefore, f and g are inverses. All right. If you do have any trouble, specifically on weird inverses like these or the problems dealing with domain for your composites, please come see me, because everything else that we kind of talked about should have been reviewed mostly from Algebra 2, but there were some tricky parts to today, so please get extra help when you need it.